Hey, welcome back. Who knows what day this is, because you get to go kind of at your own pace, but man, now that you kind of have a good grasp of Pels and where the color comes from and how electrons move when they absorb and they release, let's conveniently remind ourselves that Bohr's model, it's not the big picture, right? It's not the whole truth. It's a convenient truth. For making the jumps and the releases and absorbs and the shifts make sense. But, when we're just drawing simply like this on a, flat surface, we're equating something that's real life to 2D that's flat. And we're making it even more predictable by saying, yeah, there are these little go-karts that spin around on these tracks and they can't crash, which is convenient. And they have speeds in the lanes. So let's go a little realistic. So here's the funkiness for this. So we have to take our 2D drawing and make it go 3D, which you might say, okay, that makes sense. The moon orbits the Earth 3D, the Earth orbits the sun in 3D, but here's more the reality of it. That if I say, okay, well, you know what? Let's simplify it. Let's just talk these guys. So those electrons, I'm actually draw them right back in here because they just got obliterated. So if I got these two electrons and they're cruising around, a real 3D orbit would say you could tip that ring and spin it. It's still going to be pinned around the nucleus, but it's going to rotate and spin. Meaning, you can kind of imagine if the electrons are spinning super incredibly fast. This actually gives us the sense of a 3D shape. And one way we can kind of approximate that, at least in this case, and slash, hey, this is what you'll eventually have to start practice drawing. It'll probably take 2 videos to do that. Okay, so right now we're dealing in 2D, so like we would say, hey, there's an X and there's a Y axis. Very generic, and then hopefully not hitting too deep on geometry or algebra trauma. But to make it 3D is something you haven't really had to do. You might have occasionally drawn geometric shapes that way, but the third axis we say is Z. So there's an X, Y, and now a Z axis. Okay, so this trio, we're going to see a lot of. You're going to have to freehand these guys pretty readily, especially when we go problem to problem. Just have a backup copy here. So the funny thing is if I say, okay, we're going to draw a 3D circle, which, you might say, hey, that's a sphere. I agree. Okay, and if I do that, wow, it looks like no different, right? Because, we're still faking a 3D object in 2D. Even if you added some, cartoon shine to it, that's not realistic because we know it's not solid. We know it's not, it doesn't appear as anything. It's all electrons. And the weird thing is you might be like, okay, so if there's somewhere on the inside and it's not rings, it's more of like a playpen, where are they? Where can I track down those buggers? And here's the better answer. If you're babysitting 2 of these electrons in a playpen, sometimes they're going to be here. Sometimes you might only track 1. Sometimes they'll be moving so fast, it looks like they're in all places. Because remember, they have so little mass, they move practically at the speed of light. When you move that fast, you don't turn on the blinker, check your blind spots, and slowly shift into the next lane. You're just kind of not there anymore, and now you're someplace else. And it's so instantaneously fast. It's more realistic to think of this more like you'd think of a cloud. When the clouds are thin, you can see space between them. The color's not that strong. Sort of faded through. But the deeper it goes, the darker it goes. So when we look towards the center, I'm sure listening to this dot on the mic is great. The center is going to be thicker and deeper and denser. And then as you drift further out to the outside, it's lighter and less. Because remember, there's no actual boundary to these. There's not an actual edge of the circle. It's just you drift far enough away that it's no longer there. Kind of think of like the Earth's atmosphere. It's not a hard barrier. It's just eventually you're too far from the attraction that's holding in the atmosphere. So in this case, remember, there's still the nucleus that's holding these things in. So it also kind of makes sense to say, okay, where am I going to find them? Most likely they'll be closer to the nucleus. But here's the annoying thing. Every one of those little dots that I just thumped out there, those are all the same 2 electrons. Because now we're getting into quantum weirdness. Right? It's not just the word quantum as a packet of predetermined size of energy with a number on it that becomes a certain color. Quantum is when scale becomes so small and mass is so tiny that you start to move like a wave instead of a particle. We are giant, chunky beings, so we move definitely like a particle. We're very predictable. But if we moved much faster or lost most of our mass down to electron size, we would not really obey what would be common logic anymore. So if I say, hey, which of those dots are those 2 electrons that I drew? The reality version of the answer is yes. Or they all are. Because it's so instantaneously in one spot and in another spot at the same time that it's indistinguishable. Okay, now, I know that there's plenty of skeptics, and man, I bet you wish I was there in person that we could do some Q&A. Okay, so here is part of what we use to explain this. And so Breaking Bad fans will recognize Heisenberg. So this is the Heisenberg uncertainty principle. Notice it's PLE because this is kind of like a rule or a guideline. Okay, so funkiness for the Heisenberg uncertainty principle. Okay, so first, if we're, okay, and realize big if we're going down the rabbit hole of saying, okay, if I'm so tiny and I move so fast, I can never chase it down. Here's what that also means. If you're looking in here, you can't even promise me where the electron is at any time. Just kind of weird considering those are what hold you together and say if something burns and if it explodes or rusts and the colors that it makes. They're just constantly creating this blur. And then you go, okay, well, I should be able to catch one and prove that it's there. Okay. True. And you can, but if you do it, you've kind of killed it. You've kind of removed the property of the matter. You know, as funky as it is to say, you know, if you catch an electron in your hand, hey, what's your hand coincidentally made out of? And it's gone. It's like it never was there in the first place. But the matter keeps working. So here's what the uncertainty principle is. Okay, so this is your first quantum pill to swallow. So you can know the location of an electron, but not its speed. And we're going to use a physicsy word, we'll say velocity. Okay, meaning, hey, if you really want to know where it is, you pretty much have to shut it off. Or, if we get out the radar gun, which would be a whole bunch of like 3D charge detectors, you can know the electron's velocity, but not its location. So, if we're accepting the weirdness here, it says these things are always in motion, and while they're in motion, you don't get to know where they are, but they're going to keep doing their job. If you need to know where it is and promise or pinpoint a location, it cannot be moving, which is no longer functional. So it's this weird either or situation. Okay, and here's kind of my best way to think of visualizing it. Okay, let's go. I don't know if you guys have probably, if you've had experience, you've probably written a jet airplane, but, so this is a propeller, airplane. Okay, a turboprop takes a little while to pick up to speed, but, all right, I know I paused it, but even with the pause, you're getting some blur. I know you can point to parts of the propeller blade and say, hey, I know it's right there. I can promise you that right here, there is metal, and that's part of a propeller. Okay, but what did we have to do for you to be able to promise that you knew its location? Right, we had to shut off its velocity. We had to prevent reality from occurring. So the weirder thing is, aside from ignoring sticking your hand in there, how confident are you that you know where it is in this warbling mass of metal? And when it goes even faster, and this is just a giant piece of metal, watch the middle and bottom yellow part of the blade. And that's moving at max speed. There was metal and blade over here when we were looking at it. And the only part that you can say, well, I guess I'm kind of certain that there's metal down this strip because it looks solid. But realistically, it's in full motion and it's a blur. In fact, you're like, if you're still tripping out, like, where'd the rest of the metal go? Like, it's there. It's moving. But you don't get to know where it is anymore because it's moving at such speeds. And this is only rotating, a few, many hundred to maybe 1,000 RPMs. What if you're moving the speed of light? And what if you're so tiny that rules don't seem to apply so much to you anymore? Sorry, the slimming down part's really cool. So one more time. Yeah, that's trippy. If the fuselage, nose cone where it hooks up to is like the nucleus, right? It's kind of the center of the propeller. You're like, if I'm gambling on this, I'm most certain that there's metal in the propeller here, and you even see that thickness, right? There's certain places where it's more likely to appear. Now, for the nucleus, we think of this as attraction. In this case, this is just engineering and craziness. But the further away you go from the central focal point, the less certain you get that there's metal out there. And when you're looking at here, take would $1 million say you're confident enough to say where the metal is? I know. Super weird. Okay, so Heisenberg. You get to know one or the other, not both. So what that means is when we get back to the drawings, which if you're like, oh gosh, I thought we were just going to be drawing. Yeah, you're actually going to have to draw these when we get to the quiz. We're just going to draw it as a simple shape, and you're not going to have to do all the dots and things. Okay. But if you remember, there's 7 pels, right? So that means each ring comes in different sizes. Okay, and if you're like, oh, don't take this away from me. No, this is still true. This still holds. Okay, so if we say, what is the pel control? We know that pel is energy, and we know that energy is speed. And think of it, if you're driving a really fast vehicle, it's tough to keep a small speed or size. Higher energy is higher speed is higher size. So pels control size. Pel and energy is proportional to size. Granted, if you're doing the math here, that means there's only 7 spheres. And if you caught my drawing, only 2 electrons fit in a shape. Now that is 14 electrons. We need a heck of a lot more shapes to pull this off.